Hi, Hugh. Welcome to Devoxx. How are you today?
Good, thanks. Doing well. I hope you guys are doing well.
So, what topic have you prepared for us?
Well, it's a deep dive into Akka, and I've got a number of projects that I'll be sharing. And all these projects have what I call eye candy, which is there's a kind of a fun user interface in all these projects. So there's actually, I don't know if we're going to be able to do it in the 2 hours, but there's 6 projects, and they start from very basic to pretty advanced, like a simple Akka cluster in the beginning and an IoT application at the end. And they all have eye candy, and they're all downloadable, something that all the developers can take and try themselves.
Sound impressive. Okay, it's your time to shine on Devoxx Ukraine 2020. The mic is yours.
All right, thank you. By the way, I'm hearing another speaker though. I'm hearing Simon.
You hearing Simon? Okay, guys, organizational team, can you help us to check the sound problems with Hugh?
All right, I'll go ahead, but as long as you guys aren't hearing him.
Great, I will try to do it to help you in progress.
All right, thanks a lot.
Good luck.
All right, so hello everyone. Like I said at the beginning, I'll be doing a bunch of different projects. I've actually got a bunch of these 8 projects open, and I'm going to be trying to go through all of them. I'm going to share some links to all these different projects, and I'll show you them. But they're all on GitHub. They're all under my username McKee, and then there's a series of projects. So this is kind of the order that I'll be going through each of these projects. So it starts off from a basic Akka Typed project with a basic Akka cluster, and then each of these subsequent projects, the next 4, kind of build up on that first project, adding a little bit more features to the Akka features. And then I'm going to show you another one that's called Where on Earth. These 2 projects go together, these 2 repos go together in a single application, but they're 2 different deployments. This is a much more ambitious project. It's running in Amazon. It's running at scale, and it has a fun map-based UI. Again, all the user interface stuff that I'll be showing you is stuff that you'll be able to that come with these projects. And the READMEs cover how to do the installation and how to get things working and so on. And then finally, there's another pair of projects that I actually just got working the way I wanted yesterday. I'm very excited about that, and I'll be showing that. And this is also running in a Kubernetes environment. So the first thing I want to show you, though, is this simple project. So let me find that one. It's just Akka Typed Java cluster. So if I go back to the browser, I've got this is the GitHub repo. So it's like I said, it's just github.com, McKee, Akka Typed Java cluster. And if you clone that and then just do a Maven clean package, and then you can start running it. So I'm going to show you what this looks like here. I've already cloned the project, and once you've done I'll do it, Maven clean package. When you see to the directory, so you need Java, you need Git, you need Maven, and that's pretty much it. And I'll build the project, and then these first projects start out with some scripts because they run on your laptop or on your development system. They're fairly lightweight, but they do run an Akka cluster. So if I show you the directory here, in this project, there's a bunch of different scripts, but they all start with just this Akka script. And if I go into this Akka script, it gives all the subcommands. So there's a set of commands for doing things at the cluster level, like starting and stopping the cluster, and then opening up the eye candy piece, the dashboard. There's some commands for controlling individual nodes running in a cluster. And then I probably won't be covering this, but this one's kind of fun. And I've done some other videos on this, but this shows an Akka cluster running or where you can actually simulate a network partition or a split brain. And you can watch visually through the dashboard how the Akka cluster recovers from that. So that one's kind of cool. But really, the thing that I'll be focusing on here is these first ones, starting and stopping the cluster, and then playing around with the nodes running in the cluster. So I built this thing, so I'm going to just start a cluster, and it defaults up running 9 nodes in a cluster. Again, it's all running on my laptop. I'm just on a Mac. And it starts everything up, and I can check to make sure that it's running by just doing an Akka cluster status. It hasn't come up yet. It should come up here pretty quick. Here we go. It's starting to come up. One more. There we go. It's running. So once it's running, then you can open up the dashboard, which is just /Akka cluster dashboard. And that should, let me get the right browser window that I want to use for this. This one. So that should open up a tab here, and this shows the running cluster. So the JavaScript for this is included in this project, and the JavaScript is written specifically for this project. So it's this is a demo project, but basically we're seeing a live view of 9 nodes running in a cluster. So just kind of it's showing you what's on this dashboard. On the right side, you see this kind of matrix, this 3x3 matrix of nodes. So that represents each of the nodes in the cluster. So you can see, and I'm showing the ports because they're all running on the same localhost IP. So it's 2551, 2552, all the way up to 2559. But the way this dashboard works is that the JavaScript is polling all of the running nodes in the cluster, and it's asking each individual node, what does the cluster look like to you? So I'm jumping ahead here, but with Akka, one of the main features of Akka is that you write, you write your Akka application, you write a single application, but then you deploy that application into a cluster of nodes. So it's like you write a program that runs across a cluster, and the code in that program can talk to each other using Akka actors. And I'll show you some actor stuff in a little bit. But I want to just focus on at the cluster level here at a moment. So the view here is what does each of the 9 nodes look like in the cluster? And then on the left, it's just a kind of a view of what's called the leader. So Akka is not it's a masterless cluster type of a system. There is no master, but there is a node that's designated as the leader, and that the leader's role is only really limited to the node that makes a decision about letting nodes join the cluster or having nodes leave the cluster. And the strategy for who is the leader is quite simple. It's the node with the lowest IP and port. So when the Akka cluster is running, each node in the cluster, each of these 9 nodes are running on an IP in a different port. And when Akka goes to decide who's the leader, it's the node with the lowest IP and port. That's the basic strategy. And the reason for that is it makes it easy for every node in the cluster to figure out who should be the leader. Should I be the leader, or should somebody else be? So each node in the cluster knows what other nodes are running in the cluster, and it looks at its own list and goes, well, like so 2541 goes, yeah, I'm the leader because I'm the lowest IP and port. But 2559 looks at that list and goes, nope, I'm not the leader because I'm not the lowest. So to show you that this is actually running live, the next thing I can do is I can do I can stop a node. So I can do a Akka node stop, and I'll just stop node 5. If I go back to the dashboard, you can see it's already showing, that it's exiting, it's leaving, it's kind of a different color. and 5 is grayed out. And you saw, if you were watching, you could kind of see that the other nodes at their own time, it all happened fairly quickly, but it's not, synchronized. It's not all locked together. That the other 8 nodes running in the cluster recognized that node 9 is no longer running. So this was an example of a node leaving the cluster, and actually as the JVM was shutting itself down, there was a process initiated where the Akka code running in that JVM was signaling to the rest of the cluster, hey, I'm leaving. So it sent a message to the rest of the cluster, say, I'm leaving the cluster. So it's kind of an organized departure from the cluster. So what's happening here is all the nodes in the cluster, when they come up, they're talking to each other. It's called gossiping. Gossiping is the word for in English for talking to each other. Just chatting back and forth. So it's basically all these different nodes that are running the cluster are kind of saying, doing heartbeats. Are you there? Is everything okay? And expecting responses back. So there's all this heartbeating going on, and that's where they're gossiping with each other to kind of keep an eye on each other. Like node 2551 is gossiping with the other 7 nodes that are still running the cluster. It also was gossiping with node 5, but when node 5 said it was leaving, then it's knew to stop doing that. But another thing that you can do is a little bit more spectacular, which is I can kill a node, which is simulating a failure. So I'm going to kill, say, node 7. So this is just /akka node kill. Again, these scripts are all provided in the project. We go back to the dashboard. What we should see is node 7 went away very quickly, but then the rest of the nodes in the cluster go, oh, wait a minute, I was talking to Akka, or that node 7 a moment ago, and it was responding, but all of a sudden it stopped responding. And when that happens, the node is flagged as being unreachable. So that's what we're seeing here. And the information that we're seeing here on the dashboard is where the dashboard is polling the backend, each of these backend nodes, asking it, what do you think the cluster looks like? These are things that you can do through the Java API, fairly simple to get this information. And then I'm feeding that information back to the dashboard in the response. So the kind of a JSON response comes back from the Akka, the Java code that says, yeah, well, this is what the cluster looks like to me, the 2551, or to me, 2556. It's we got one node that's no longer there and another node that's unreachable. The other thing that got flagged is that I'm showing the L. The L represents where the leader is at, and also in the top left, you can see the leader is on port 2551, which is the lowest IP port, but it's shown in red. And what that means is that the leader is in a state where it knows that there's something wrong with the cluster. And this has significance because a leader is supposed to be the one that promotes nodes to be running in the cluster, being in an up state, and allows nodes to leave. So I'll show you what that means if I try and restart node 5. So I'm going to do Akka node, just type node start 5. Back to the dashboard. So we should see 5 come up as joining, and then it goes into a weekly ups. So what I'm showing in the dashboard is the state of each node, and there's a life cycle that nodes go through, and that life cycle is defined in the Akka documentation. But really, what's happening here is that this node is running. It's asked to join the cluster, but the leader is not able to let this node go to a fully up state. So that's why I'm showing it as a darker green, to kind of make it clear on the dashboard that this node is trying to join the cluster, but it's not fully up. And this has a significance in many of the things that happen because Akka also is an actor system, the actor model. I haven't really talked about that yet, but actors run on different nodes in the cluster. And in many cases, you don't want actors running on nodes that are not fully up. So this is kind of an important state. So a lot of the built-in actors that come from Akka, for example, really keep an eye on this so that they don't say allow traffic to start flowing to this node until it's fully up. So to fix this, I need to resolve this issue that this node is unreachable. So the way to do that is you can down a node. So I'm going to go and do a Akka node down 7. Now these scripts are something I wrote. They're just part of the this project. If you look at the source code of these scripts, you can see how this is actually being done. I just added these scripts to make some of this stuff easier to do in a demo situation, and more importantly, easier for you guys to do if you want to play around this. So I'm going to send in the down, go back over to the dashboard, and right away you saw 5 go up because node 7 was down. So now it's no longer red; it's just gone. So now we're up. We're up and running, and we've got the 8 nodes running. We don't have anybody down. The leader is not red anymore. The leader is happy because all the nodes running in the cluster are in good shape. And there you go. So let me just, I'll just for fun start Akka node 7. And see if we can watch that come into the cluster. There goes joining, and then it's up. Again, you can kind of see the up state kind of propagate through the other nodes in the cluster. And this was a fun part about doing this dashboard, was having it do the constant polling. It's polling about every 200 milliseconds, each of the nodes in the cluster, asking it for what does the cluster look like to you. So that's where you're seeing it. It kind of takes some time. It doesn't. They all don't change at once, but we're looking at a live system. So let's take a look at the project. So this is, like I said, it's I downloaded this project, the AkkaTyped Java cluster, and there's just a few classes in here. This is a very, very basic project, and it's just got 3 Java classes. There's a main, which is where things start. The main method is in this class. There's a HTTP server class, and that's used for the dashboard. And then there's a cluster listener actor, and this one is kind of a basic actor that I'll show you. But it's kind of it's an example of a simple actor. Let me go into main first. Let me get this guy out of the way. Hopefully my font is big enough for you guys. So in the main method down here, it just does a few things, and it starts up an actor system on this line, and this is how you start Akka. Basically, you start an actor system, and I often explain this as it's kind of a there's not a lot of code involved, but it does a whole bunch of stuff. It's like a glorified thread pull in a way. But this is what it takes to start Akka. Now, part of this process, though, is that I'm creating what's called the root actor or the main actor. So Akka actors can create other actors, can create other actors, can create other actors. So you have an actor system that forms a hierarchy, and that hierarchy has a root, and the root starts with this, with a supplied main actor. If you've done Akka in the past, before Akka Typed, it's called Akka Classic now, there was a different process, but this is all Akka Typed. And one thing I do is I invoke a method that does a little bit of configuration setup. which is, not too much here. It's kind of setting things up. There's this project in the documentation and README explains how to do it, but you can set it up to run on localhost 1 and localhost 2, 127.0.0.1 and 127.0.0.2. There's some other commands that are provided in the script, but this is the kind of setup running the 9 nodes in the cluster where the first 5 nodes run on localhost 1 and the last 4 nodes run on localhost 2. And the reason for that is to set up a network partition where we actually block network traffic between localhost 1 and localhost 2, which triggers a network partition, which triggers a split brain, and and you can watch it in the dashboard. So I'm not doing that here, but this is what you're seeing in this code here, this setup cluster node config method. But this class is starting up a very simple actor up here, and because I'm doing the main create, and in the create, this is a basically just invoking a method where it's setting up a behavior, and the behavior is defining how an actor responds to messages. So with an actor, actors are really interesting. In fact, if you look up the actor model and go to Wikipedia, it's got an outstanding, concise definition of the actor model and actors in it. So that's a really good source to start with if you're brand new to actors, you've never used an actor type of a system. But fundamentally with actors, and I'll show you, you write them as regular classes on, this is all Java, you can use Scala as well. And the main difference is that no external code directly invokes any of the code within an actor. The only way you can communicate with an actor is to send it messages. So a behavior is defining how this actor handles messages. And actors can have different behaviors depending on the actor's state. So as an example, say you have a simple actor who can be either in an idle state or a busy state. So when it's an idle state, it's ready to accept requests to become busy. But when it's in a busy state, it is going to ignore requests to become busy because it's already busy. And the way you do that is actually fairly simple using these different behaviors. So an actor can have an idle behavior saying, yep, when I get a message that says, I want you to do this task, it goes, yeah, cool, I'm going to do this task, and it's going to kind of switch from an idle state into an active state, which means it switches behavior from an idle behavior to an active behavior. So this is what behaviors do, is you're defining when you receive messages, which is starts right here. I'm creating a behavior, and you define as messages come in, what does this thing do? Like, what method does it invoke, basically? So this is a real simple one. This actor is really not doing anything other than bootstrapping the rest of the cluster. And as an example, it's calling this bootstrap method, and all this bootstrap method is doing is spawning another actor. So this is the beginning of the hierarchy. This main actor is a root actor, and it's creating one actor as a child actor to it, which is the cluster listener actor. So this is how I'm kind of bootstrapping this system. When we get deeper into some of the other projects, this will get a little bit more involved. But here I wanted to have this project, like if you want to start a basic AkkaCluster project, or you want to see one and kind of examine what's going on, and with just a few actors, with not a lot of other crap, to be honest, that just makes it hard to kind of grok what's going on, then this is a project for you. Start it up. It's very basic, but it also has this kind of cool dashboard that comes with it. So let's take a look at this cluster listener actor, because this actor is a little bit more interesting. So start out, the cluster listener actor, it extends a base class, and so it's extending what's called abstract behavior. And this is where the typing comes in, where the actor says what types, by class types, will this actor accept as messages. So here it's saying I'll accept messages that are of type cluster event, cluster domain event, which is actually an Akka class. And then in the behaviors, do a setup, getting down in there's typically the pattern is you have a create method, and the create method, it gets invoked in static, and it actually sets up the behavior, which basically here I'm just doing the setup is going to create an instance of this class. So I invoke the constructor down here. The constructor is past the what's called the actor context. So this is kind of context information about this actor. This actor context has quite a few methods on it where you can get information about this actor, and things like its what its actor URL is, or it's what's called an actor reference, and other things. But the main thing this guy is doing is in this method is it's invoking this method called subscribe to cluster events. And down in the subscribe to cluster events, it's using an Akka API to create a subscription. And this line is where it's actually sending a message to this other thing, this other actor, saying, hey, I want to subscribe to cluster events. So this is the first example in code where one actor is sending a message to another actor. It's called a tell. And you'll often see this in Akka Typed, where when you have your actors that are interacting with Akka, you're typically not invoking some kind of an API. You're sending messages to Akka saying, what you're requesting. And then you might get messages back with some kind of response. Now, so here we're just, what I'm doing is I want to subscribe to cluster events. That's why I call this a cluster listener actor. This actor is listening to, it's written to listen to cluster events. So what are cluster events? Well, cluster events are things like other nodes in the cluster joining the cluster or leaving the cluster or becoming unreachable. So as I get further into code, all I'm doing in this actor is I'm getting those cluster events and I'm logging them out. So moving on, there's only one method that I need to implement from the base class, this abstract behavior, which is right here. And it's this create receive. And this is how you define it, yet again, what does this actor do when it receives messages? So in this case, I'm saying on any message, limited to the types that I've specified when I define the actor, I'm just going to invoke this method called log cluster event, which is right down here. So this log cluster event gets this, this message. So the message that was sent to this actor is when this log cluster event method is invoked, that message is passed to this method. So I just log it out, and I put some other information in the log message, like sent to, this event was sent to this node in the cluster, and then I invoke this method called log cluster members. This is a little bit more involved, but basically I'm just doing a little bit of Akka magic, using the some of the Akka API, because I've registered with some of this, and I'm logging out the nodes in the cluster. So that's pretty much it. I don't want to get too much into this. There's a lot of code here, but sorry about this. But there's this gets a little bit deeper in, and maybe if I have time, we'll come back to this. But really what I'm doing in here is I'm getting some information about each node in the cluster, and then logging it out. I'm just looping through it. So we can see this if log files from this cluster are written to the temp directory. So I can do just do a less on temp, and I'll just go and look at this log. If I do a search on, we can see some of the log messages coming out from the cluster listener actor. Let me get down to where it's more interesting. In fact, let me go to the end of the file and go backwards. It's hard to read. There's a place where it lists out all the nodes in order when I've got the text. Here it is. You can see it here. So it's listing out. It's in that loop, and it's listing out. Member up. It was the message that it got, and then it goes in and it says, all right, how many nodes are in the cluster? Oh, there's all 9. So it just lists them out 1 through 9. You can see here, and that this node information just kind of shows the cluster address, the node address, and then its state. Is it up or down or joining? Things like that. If go back a little bit further, we might see. Let's see. Yeah, see, here's one where the state of the node was joining, and not all the nodes had, the nodes were coming up and they were joining. So when I first started this project, I had just the logging here, but it was like, man, this is boring. Really would like to have the dashboard. So that's what motivated me to write this dashboard, so we can watch the cluster kind of come up without having to pour through a bunch of log files. You can see it live and things like that. It was a lot of fun to write this, and I'll show you a little bit about the source code and how this is done in just a moment. But that's kind of it. This cluster listener actor, it just sends one message to Akka, but then it sits there and it receives messages from Akka. So as the state of the cluster changes, which is kind of cool, Akka is sending this actor messages saying, hey, this member is leaving or joining or whatever's going on in the cluster, and I just, that triggers an action in my actor here to go through this code I wrote that logs it out, basically. So the other thing I'm going to show you is the other thing, the HTTP server actor. So this HTTP server actor is using Akka HTTP is called. And it's getting, different. It's set up to handle different incoming requests. So it handles the incoming requests for the HTML, the JavaScript from the HTML. There's 2 JavaScript files. There's one I wrote, which is called dashboard.js. And then this dashboard is written using a very cool library called P5.js. And a favicon, and then this cluster state, though, is the one that's fun, because when a cluster state request comes in from the JavaScript, that invokes a method which gets the cluster state. So the action really starts down here in this load nodes. This is, again, gets kind of involved, and I'll leave it to you to take a look at it. But what I'm doing in this method is I'm basically going through, and I'm just using the Akka API. So the first thing I say is, using the actor system, I want to get what's called a cluster. And from the cluster, I want to get the cluster state. And then from the cluster state, I can get all kinds of information. So first I can give me the list of unreachable nodes. Are there any unreachable nodes right now? And it gives me back a set of what are called members. And then I do a little bit of streaming, and I go through a stream where I go to the cluster state again. I get all the members, and I just do a splitter array to get a stream of members. And then for the members, I do a little bit of filtering. Is the member up, and is the member not reachable? things like that. And then I just reduce it down to what I'm trying to get is who's the oldest node in the cluster, which I haven't talked about yet. But I'm kind of filtering through the unreachable and the current members up members in the cluster to find out who's the oldest nodes, because I want to know what the oldest node one is, because I want to show that on the dashboard. And then I can give some other information, but then the next part is where I kind of build the full object that I'm going to send back to the browser, starting in this line, where I get the members, I create a stream, and then I just go through a consumer where I'm building up a list of nodes. And then this is how I'm returning that information back to the dashboard JavaScript. So the dashboard JavaScript is, like I said, is pinging all 9 nodes. Either if it gets a response back, then it uses the JSON that it got back to render that in the dashboard. And that's the main part of what this HTTP guy does. The other part was where's the routes? Like feeding back the files that are part of this project, like dashboard HTML, the JavaScript. Those are all in the resources. Like here's the JavaScript, the dashboard JavaScript, the HTML, the P5.js code, and it's not minimized. I'm not really worried about performance in this demo app. While we're here, another thing I want to show you though is a file called application.conf, and this is using the type-safe config stuff for configuration. And this file is as minimal as possible for this application, so it's pretty light. I just wanted to have enough of a configuration so that I could run an Akka cluster and no more. Don't need any more drama than that's already there. So one thing I usually add to my config file is this log config on start, and you can set it on or off. When you set it on, you see all the config settings get dumped to the log file, and it's quite a lot. So normally I have this off unless I'm doing some debug on what actually is set in the config. But in the config, in order to run a cluster, I need to set this, say the provider is a cluster. And then another thing I'm doing here is when you're not running in a dynamic IP environment, you set seed nodes. And the seed nodes are used when the cluster starts up. Let me go back to the dashboard. So as each node in the cluster starts up, what happens is they look at their config and they go, am I a seed node or not? If I'm a seed node, then I'm expecting other nodes to reach out to me to ask to join the cluster. So these first 2 nodes are seed nodes. You can see that here, up in the dashboard, it says seed node on these first 2. So when, say, 2554 started up, it's each one of these is a JVM. Each JVM runs, it starts up, it grabs this config, it takes a look and goes, oh, I'm not a seed node, but 2551 is a seed node. So I'm going to send a message to 2551 saying, I'd like to join the cluster. And then they start talking back and forth, and if everything's cool, then it's allowed to join the cluster. So off we go. So that's what's going on in the seed nodes. I've got the split brain, what's called the split brain resolver. I've got this commented out because if I kill a node, I manually downed it when I showed you a few minutes ago. If I had the split brain resolver enabled, it would have downed it automatically. And there's a configuration setting for how long the split brain resolver will wait before it reacts. And the default is, I think it's 10 seconds. I increased it to 15 seconds when I'm using that for demonstrating a split brain. But in this case, I'm not demonstrating a split brain. And then finally, there's one part for what's called Akka management, and I'm defining, there's an HTTP port where you can hit for Akka management. And some of those scripts that I'm using use the Akka management port. They send curl commands to this port for, like downing a node, for example, goes through 855 whatever this port gets configured to be. So that's kind of it. I want to move on though, because I spent a fair amount of time on that guy, on this project. I want to move on to the next one. So I'm going to stop this cluster and we'll watch it stop. So stop, I'll go back to the dashboard. You can see everybody's leaving. It takes a little bit while all the JVMs shut down. And then, all right, we're down. So that cluster is down. So let's move on to the next project, which is Akka Cluster Aware. So I'm going to go to that guy. And I'm just going to go ahead and start up the cluster, get things rolling as quickly as possible. Start the nodes, check on the status. There's no point in trying to open the dashboard until the cluster is up and running. So this status script is kind of a convenience for seeing has the cluster gotten itself in reasonable shape. Okay, we got a cluster running. Set the dashboard. And this is going to be a little different. There we go. So it's a similar dashboard, but now there's a little bit more of the empty spaces in use. And you can see things are happening. So what's going on here is that I took that first project and now I've added in, I created a new project, but now I've added a little bit more to it. So what's happening here is there's actors that are talking back and forth to each other. So what's going on is there's a new actor that I've added that's aware of the fact that it's running in the cluster, and it's aware of the fact that it has a clone of itself, itself running on each node in the cluster. So each of these actors are sending messages back and forth to each other, and that's what these counters are showing here. So this actor on 2551, what it's doing is it's sending messages to its counterparts on all the other nodes on the cluster. So it sent a message to the actor on 2552. When that actor gets that message, it simply sends a response back. It sends a message back to the first actor saying, "Yep, I got your message." So, and the messages are actually called ping pong, which is a game like table tennis or whatever it's called, ping pong. So when I'm showing it, kind of animating here, is the count of the number of messages that are getting ping pong back and forth between all these different actors. And I thought it would be kind of fun to show that this is happening. So already, just the short time that this guy's running, the actor on 2501 is sent almost 20,000 messages, and so have the other ones. So it's kind of the rates are all kind of random. I'm showing the rate, like the 162 messages per second, 175 messages per second, and so on. So again, it's same as the last project, but with a little bit more added to the dashboard. A totally different project though. It's this Akka Typed Java Cluster Aware, or Akka Typed. I don't know. I have to look at the project name again. Akka Typed Java Cluster Aware is the project name. So let's take a look at the code in this guy. I'm going to go find that project. Here it is. So it should be somewhat familiar territory. There's a main, got an HTTP server, but we got a couple new things. An HTTP server actor, there's the cluster listener actor, just like the prior project is there, and then there's this cluster aware actor. But let's look at the main, because it's just a little bit different. So in the main, what's going on is it's doing its bootstrap. It's starting up the cluster listener actor. But then it also starts up two other actors, an HTTP server actor and a cluster aware actor. And the reason for this is that the cluster aware actor all the cluster aware actors need to report statistics. I got to feed all these statistics that are happening up to the dashboard. And all those statistics are, of course, reachable via the HTTP server. So I got to, feed all that stuff. So I'm going to go into this cluster aware actor. And starts out, it's another, it extends the abstract behavior. It bootstraps itself, and I want to just show you this create receive. This is where you define the what messages or how it's going to handle what messages it is going to take. And there's some message called listeners. I'll explain that in a bit. There's another message called tick. I'll explain that in a bit. And then here's the ping pong. So this describes, when this actor receives a ping message, it invokes this onPing method. When this actor receives a pong message, it invokes this onPong method. So how does this actor work, though? Well, when it starts up, it does a couple things. So back in the constructor here of this actor, which is invoked when the actor is created through the static create method, the actor is passed in the HTTP server. It's called an actor ref. And an actor ref is like an actor URL. So if one actor wants to send a message to another actor, it sends a message indirectly, as I mentioned earlier, and it sends it via this actor ref or actor URL. So when you create an actor, the spawn operation returns the actor ref for that instance of that actor that was just created. So when I created that HTTP server actor, I saved the actor reference so I could pass it on to this cluster aware actor, or this aware actor, and because this actor wants to send messages to that other actor. So I save that, but then there's this register and subscribe. So what's going on here? This is a pretty cool feature. There's a feature now in Akka, and this gets more into the deep dive. It's a relatively new feature with Akka Typed. It's called the receptionist. And with the receptionist, what it is that it allows other actors to subscribe to actors that register with the receptionist. So you can have some actors that register and some actors that subscribe, or you can have some actors that register and subscribe. So in this case, I have an actor who's registering and subscribing. So with this receptionist, which is fairly easy to get, the actor context, get the actor system, and then get the receptionist. This gives me a reference to the receptionist. In this line, I'm sending a message to the receptionist saying, hey, I want to register myself, context get self, which is my actor reference. And I want to register myself using this service key. So service key is a way for subscribers to group themselves. So you could have multiple groups of subscribers, and all the subscribers kind of form themselves into a group. It's kind of like a chat room in a way, what's going on here. So on every node in the cluster, when this actor starts up, it's registering and saying, I want to join this group defined by the service key. And here's my actor reference, my actor URL. So right now what's happened is 9 actors have registered with the receptionist. And then the other operation here, subscribing, what that tells the receptionist that send me the list of who's registered every time somebody new joins the list or every time somebody leaves the list. So that's why I'm subscribing to this. And that sets up the receptionist then will send this actor messages with a list of who's currently subscribed through this message, this listeners class. And it's basically a list that's coming back, a set. And that tells this actor, gives it this actor, who are the other subscribers? Who are the other actors like me in my service key group that I can ping pong with? So that's what's going on here. Now the tick one is also interesting. The tick is a timer. It used for a timer, because when I set this actor up in the create method, one of the things you can do is you can set up a behavior and with it what's called a timer. And this timer is passed into a lambda, which I just use to pass to my constructor. So this timer here is just where you can schedule things. So with the timer on this line, I'm just saying, all right, and you kind of tell what this actor is doing is telling Akka, I want to schedule sending a message, this tick instance at this interval. I want to send it to myself. So the reason I'm doing this is that I've used this to send a message to this actor to trigger it to send messages to the other actors, and it's happening at some kind of a rate. And the tick interval is where do I define that? Here's a tick interval, and I kind of do a random on it within a range, and I'm looking for a range of around 50 milliseconds. So it's like from 25 to 75 millisecond range. So I kind of randomize how often, but the tick interval that each of these actors start up with, roughly around 50 milliseconds. So every 50 milliseconds, it gets a tick message. And if we go into the onTick method, what it does is it pings up colleagues. And I'll show you that method in a moment. But basically, this is the mechanics of it, sending messages to the other nodes in the cluster, the other actors running on the other nodes in the cluster. So this ping up colleagues, a little bit more involved. Won't dwell on it too much because just for the sake of time. But basically, I'm just looking for the other members in the cluster that are up, and I want to send a ping message to those guys. So at some point, where do we see the tell? Where's the tell? Sorry, I'm looking for where the tell is in this guy. There it is. Yeah, sorry, it's kind of buried a little bit deep here. So it's going through the stream, do a little bit of filtering, and then here's where the actual tell is at, where it's doing sending a message using that list that came from the receptionist, and it's sending a new ping message to that other actor. So this is how every about 50 milliseconds, this guy is sending a message to one of the other, or all the other actors on the cluster. In the stream, I'm filtering out myself. So, and then also making sure that the other things that I'm talking to are up. So if so that happens on a tick. So when an actor gets a ping message, it invokes this method. I do a bit of logging, and then I reply to the pinger with a pong message saying, "Yep, I got your message. Here's my reply." And then I capture up some statistics, which are then I use that to periodically send to the HTTP server. So let me go back to the system here. This list here then is coming from the receptionist in each of these actors. So if I stop one of these nodes, I'm going to stop node 1 this time, and I'll show you what's going on there. Akka node stop 1. Here goes, it's going down, and then you should see these lists shorten when node is down. So yeah, they all shorten by 1. So if you look, 2551 is no longer in this list, in any of the lists here, because all these other actors were notified that a subscriber left the receptionist, that node is no longer there. So they know not to stop send messages to them anymore. It's not capturing any statistics from them anymore. And so the list adjusts. But I deliberately stopped node 1 as well to kind of go off on a side for a moment to talk about the oldest. And because I'll be getting into that in the next project. But notice that the oldest used to be, the leader and the oldest used to be node 1. And so the leader, 2552, is now the lowest IP in port. But the oldest, it happens to be, and it's just kind of random, it happens to be that now the oldest node in the cluster is 2555. Well, the significance of the oldest is where what's called a cluster singleton works, and we'll be looking at that in the next project here in just a moment. So, but these things move around. So if I start up node 1 again, though, let's start 1. We should see node 1 come back up. Like there it goes, it's joining. And then we should see the lists update. So now the lists go back to, 2551 is there, 2551. All the guys, other actors in these clusterware actors in the system see this. So all these statistics that we're seeing here are being sent in from the clusterware actor on node 2554, for example, or on node 2555. And they're all being fed to the web server via that web server actor. And notice now also started up node 1, the leader moved back, but the oldest didn't change because the leader is the newest node in the cluster. So that's not going to impact what is the oldest node. So the idea of the oldest node is it's the most stable node. So things that we'd like to keep running or keep as stable as possible, like cluster singletons, the idea is let's put them on what seems to be currently the most stable node in the cluster, the one that's been around the longest. So that's cluster aware. The receptionist is a very powerful. This is kind of opening up the cluster to you. I just wrote this code, and it's a simple, basic example of actors talking to each other across the cluster and how to do it. The basic code to make it happen is very straightforward. The Akka documentation, if you look for Akka receptionist, is pretty well documented. It's pretty easy to follow. It's definitely getting to a more advanced technique, but I think it's a very powerful technique that's not, like super rocket science. So let's move on to the next project. Got to pick up the pace here. So first I need to stop this project, or stop the cluster in this project. So we'll make sure it stops. All right, it's down. Close this tab. And go back to code, and we'll find the singleton. That is singleton. All right, so the singleton project, third project in this series, takes the second project and adds a little bit more to it. And so let me show you this one running. Now I go to the command window. So I got to change directories to the singleton. And I'm going to start the cluster. Status. It's up. Come on, buddy. Here we go. And open up the dashboard. All right, so now dashboard's running, same dashboard, but now there's even more. So the cluster aware actors are still in this project. They're still ping-ponging back and forth to each other. So the dashboard's getting a little bit more interesting. And now I've filled in the last big empty space in the dashboard here. And what this is showing is it's showing what I'm calling singleton aware actors. So what's a cluster singleton? A cluster singleton is an instance of an actor where there can only be one instance of that actor across the cluster. And why would we do that? Well, maybe you have to have an actor that has to make cluster-wide decisions, and you don't want to have to go through any kind of, say, distributed negotiation about what the decision is between, say, multiple parties, like multiple actors. You just want to have one actor that can make that that decision. But so how do you handle that? Well, there's this really convenient pattern in Akka for having a singleton actor, and that's what I've done here. So what's going on is the singleton actors, and you can have more than one singleton actor. In fact, it's very common that, Akka uses singleton actors, and of course we can write our own singleton actors for our own applications. But the singleton actors always run on the oldest node. This again is the significance of the oldest. So same thing's going on though, is that there are actors, individual actors on each one of these 9 nodes that are sending messages to the singleton actor. It's a ping message again. And then the singleton actor is getting those ping messages and sending back pong messages. But now all I'm showing is counters from the perspective of the singleton actor. So the singleton actor, what I'm showing here is so far it's received 25,000, 26,000 messages from these other actors, these other 8 actors, or I'm sorry, 9 actors, one actor per node in the cluster. So if I stop one of the other nodes in the cluster, like I'll stop, let's say, node 9 for fun. It's leaving, it's exiting. It should be gone. The lists get updated, and now all the lists, including the singletons list, is updated. Now we see we're not receiving messages from 2559 anymore because, of course, it's down. So the singleton actor is aware of that. It's just keeping track of who's sending it messages. Now, the next thing I'm going to do though is I'm going to stop node 1, which is going to stop this actor. And you can see the state of this actor right now. It's got a count of like 37,000 messages. But let's see what happens when I stop node 1. So node 1 is leaving, it's exiting. Now look what happened. The counts in the singleton actor are reset. Because I'm not persisting this anywhere. I'm not saving this information. I did this deliberately because I wanted to show that unless you're doing some kind of state persistence, maybe to some kind of a database or something, that when the singleton actor used to be running on node 1, and now apparently it's running on node 3, 2553. And when that happened, a new instance of that singleton actor was automatically started up. I don't have to write any code as a programmer to do this. An instance of my actor was started up somewhere in the cluster. So in this case, it's on node 3. Everything keeps going. Everybody's, they're all talking to each other. And then now if I start back up nodes 1 and 9, just to get back to a full complement, 1 and 9. See these 2 nodes start up. The list should get longer here. There it goes. The lists are filling out. And the singleton didn't move though, right? Because now this is the oldest. Even we have 2 new nodes, so these are very young nodes, nodes 1 and 9. So it's certainly not going to. I don't want that. We don't want that to trigger moving the singleton when new nodes join. We want the singleton to be as stable as possible. So that's kind of what's showing you. The counter kept going uninterrupted, and things are happening. So if we go into the project, I'm just going to jump. Well, let me see. I'm going to in the main. I'm going to show you how. It's not in the main. The singleton actor is started. Well, there's actually two actors. There's a singleton aware actor, and then there's a singleton actor. So let's jump to the singleton aware actor. So in the singleton aware actor, the thing I want to show you is, it goes through the normal thing. There's a static method to do a create that invokes the constructor of the class, passing it things like the actor context. This guy has a timer, and it also has, let me get this out of the way, the HTTP server reference, because this actor was also feeding statistics to the HTTP server. But the interesting part is here, where this is how the singleton, what it takes to set up the singleton actor. Just do there's a cluster singleton class, do a get with the actor system, and then there's a init method. And then init method, I'm just saying, give me a singleton of cluster singleton actor create, and I'm passing it I'm just giving it a name, that this cluster singleton actor class gets simple name. So it's just kind of an actor name. So on every node in the cluster, there's this singleton aware actor, which is invoking the code that initializes cluster singleton on that node. So on each node, this happens, but then the nodes themselves, Akka negotiates, right, where does the create method actually get invoked? It's only going to start this actor on the node that's currently the oldest node. So it's not going to start this actor on all 9 nodes in this running cluster. It's only going to start this actor once in the oldest node. And then, because we've initialized it, giving it this information about how to create the singleton actor, when the singleton has to move because the node it was on is gone, then it again goes, oh, we lost the oldest node. A negotiation goes on. This is all in Akka. It figures out, here's the new oldest node, and then this cluster singleton create method is invoked on that oldest node to start up a new instance of the singleton on the new node in the cluster. And then this guy's just doing, it's sending out ping messages and receiving back pong messages. So that's what's going on here. So it's very similar to the cluster aware actor. The dashboard showing the statistics here. So this dashboard's kind of filled up. This was my goal at the beginning, was to kind of show some activity, going on, but there's more. So I'm going to move on to the next project. So let me stop this cluster. The next one's a lot of fun as well. So this project's stopping. There it goes. Everybody's gone. I'm going to close that. And I'm going to switch to it's called sharding, cluster sharding. And I'm going to switch to the project as well. AkkaCluster. Sharding. Yep, this is it. All right. So now that we've switched over, I'm going to start this cluster. Wait for the status. Okay. And then I'll open up the dashboard. So you might have guessed this project has everything from the last project, from the singleton project, which has everything from the second project, the Aware project, which has everything from the first project, but it has more. And so we got, the cluster aware actors talking to each other through the Akka receptionist. We got the cluster singleton working in this one, but we also have cluster sharding working. And this one's kind of fun. It has a different view, and it's actually called viewer. So it's Akka cluster viewer. This time I'm going to give it a node number. I'm going to give it node 2, and I'll show you why when it starts up. So I'm starting it up on a different HTTP server. So this one's kind of cool. It's called somebody internally at Lightband, when they first saw this, they called it the crop circle. I don't know if everybody knows what a crop circle is. Crop circles are kind of famous in different parts of the world. What happens is that somebody comes into like a wheat field and creates an elaborate pattern. Very elaborate patterns. If you do a search on crop circle, you'll see, and look at the images, you'll see this. And there's these really elaborate patterns, and they're supposedly from aliens, from people off Earth, people, UFOs, things like that. But really, it's very clever. Well, at least this is my opinion. It's very clever and talented people being funny by creating these, and a lot of spare time in their hand, creating these elaborate crop circle things. But anyways, this is a view of cluster sharding. So what's cluster sharding? Well, cluster sharding is a way for distributing work of stateful actors across a cluster. So this diagram is showing, up in the top left, is showing kind of something similar. This is a little familiar since you've been looking at the dashboard, that we're running on 9 nodes and they're all green and they're all up. But this new diagram here is showing these big circles represent the 9 nodes. And then these little circles on the perimeter represent individual entities. So you can think of an entity as, say, a shopping cart. Like, say you're in a shopping cart. So this is your shopping cart. I'm in a shopping cart, and this is my shopping cart over here. Somebody else is in a different shopping cart, and they're in a different shopping cart. But these represent stateful actors that have the state of your shopping cart in your actor, in my shopping cart, in my actor, and everybody else's shopping cart in other actors. So right now, there's a bunch of these different entity actors that are running across the cluster. And when I mouse over, you can I make it bigger. Each individual entity actor has an ID, which is usually like the primary key of the entity. So an entity is, think of it from a database standpoint, an entity is the thing, right? The shopping cart and all the data structures that are associated with the shopping cart, like, the customer information, items in the cart, shipping address, billing address, all that kind of stuff, billing information. That's kind of, the state of the shopping cart. That state can be maintained in these actors. But the trick is distributing this work across the cluster. And I have a brand new version that I just got working the way I wanted yesterday that I'll show you in a few minutes that goes into some more detail on this. But right now, I just want to show you a few things here. So you can see that these big circles have smaller circles out from them. And these smaller circles are called shards. So if you ever heard of things like database sharding, this is exactly the same process that's going on. And what the shards are used is to distribute actors across the cluster. Now, the number of shards is configurable and it's fixed. So in this case, there's, I think I've got 18 shards in this configuration. And there's 18 because there's 2, you can see there's 2 shards per node in the cluster. But there's always going to be 18 shards, but there might not always be 9 nodes. So I'm going to stop a couple of nodes in this cluster and show you what happens. Actually, before I do that, I want to go back and show you another thing. I'm going to stop node 7. So I'm going to flag one of these entity actors. See, it turned red. I clicked it, and that'll turn that one red. So it flags. I'm going to kind of trace this actor 2556-4 and I'm going to trace shard 1, which currently happens to be running on node 7. So I'm going to stop 7, and I'll stop and I'll stop node 1, because node 1 is shown in purple because that's where the cluster singleton's at. The reason why node 2 is a different color is this is where my browser is hitting. Which node is my browser hitting? And the reason for this is that if I click a node here, it's going to stop that node in the cluster. So I'm just going to click it, and we should see that node shut down here. There it goes. So node 7's gone. But notice right away, shard 1 already has moved to a different node in the cluster. And now that node now has 3 shards versus 1. And there's our actor. The actor got restarted on this different node. So this is where Akka is built to be resilient. It's like in its DNA to be able to handle these kinds of things. This poor little actor was running along on node 7, doing its thing, had all of its state and memory, everything was cool, and then bam, node 7 went away for some reason. Maybe it failed, maybe it was scaled back, who knows, who cares? But what Akka does is okay, fine, no problem. When a message gets sent to this actor again, or any actor that belongs to the shard's going to be recreated, and all the associated actors will pop up as they receive messages on this new node in the cluster. And then I'll do it again. We'll trace another actor over here. Say, let's see if I can get it. 255.4-6, and on shard 7, and I'm going to stop the node with the oldest on it, and we should see the shard move, the actor move, and the singleton move. So the singleton pops up on node 3, and then we should see the shard pop up here. There it is. It pops up on node 5, and then there's our actor. So now this actor has also moved. Now, but when I say moved, of course the actor that was running on the node I shut down is gone, right? It was in memory on that other system, but now it's gone. So the actor had to be restarted on another node in the cluster. But this is how quickly Akka adapts to this. So what's happening is as the cluster scales in or scales out or has some kind of a node failure or whatever it is, the cluster adapts to it. So this project comes basically with these 2 dashboards. It comes with the familiar dashboard from the cluster singleton, and where we're seeing also the same thing that nodes 1 and 7 are no longer running. But now it also has this dashboard that is kind of visually representing cluster sharding and how actors are distributed across the cluster. And in another project I'll show you in a little bit, kind of takes things a step further, but that project's running in a Kubernetes environment. So this one's a little definitely more lightweight. Again, you can just clone it, Maven clean package it, and then use the Akka scripts to run it and play around with it. And that's all you really need to do it. The rest of the project I'll be showing you in a few minutes are going to be ones that run in Kubernetes, Akka running in Kubernetes. So anyways, let's look at this project. In the main should be somewhat familiar, but it's getting a little bit more crowded because we're starting up more actors. And we got the cluster aware actor that we're starting. We got the cluster singleton actor, but then there's these 2 other actors, which are entity command actor and entity query actor. So what these actors are doing is they're just sending out random messages to entity actors. So these are kind of simulators of traffic. So I didn't want to have like an external HTTP tester or something like that, which you could do, but I wanted to make this project simple, standalone, clone it, build it, run it, and play with it. And then not a lot of ceremony or drama to get it going. So these guys are just, they're using timers to send out messages periodically to entity actors. So that's the entity actors is set up with this in this cluster sharding method, which I'm going to go to here. So this is all the code that's needed to start up cluster sharding. Just to do a cluster sharding get actor system. This pattern should be familiar, like cluster singleton get actor system and so on. We did that before. And then you do a cluster sharding init. And basically what we're passing here is what is the actor that's used to handle entities. And in this case, it's an actor that I wrote called an entity actor. And I'm just doing a create. And again, I'm passing it the actor reference to the HTTP server actor because I want these actors to feed statistics to the HTTP server. This is it. This is all the code that I need to set up cluster sharding. And then if we look at the entity actor is, in this case, it's just another actor that extends abstract behavior. It's a little bit more involved, where it's getting some more information, but it's it's got a create method, which invokes the constructor of the class, and then there's a create receive method, which we have to override and implement. How are you going to handle our incoming messages? So the incoming messages are 3. There's on change value and on get value. So these are the messages that are being sent by those other 2 classes. Let me go back to the main. This command actor and this query actor. The command actor is sending command messages, and the query actor is sending query messages. And the entity actor is receiving those messages. So when it receives those messages, like when it gets a on change value, which is the command, go to that method, and all it's doing is this actor has a very simple state. When the actor first starts up, the state is null. And then once it receives a message, then it initializes its state. And from that point on, it has some state. There's no persistence or anything like that going on in this actor. No database yet. So I log it out, that it was initialized, but then here it send back a reply to the actor that sent me this message saying, yep, it's an acknowledgement. I've initialized myself. Or if it's already alive and it's stateful in memory, then it just sends back a reply of, yep, I've just updated myself. That's it. The other thing, though, is that when it's initialized, I invoke this method called notify HTTP server. And I create this, what I call broadcast message, which goes to the HTTP server actor. And the HTTP server actor then gets this message. So before I go into the code, I want to show you what's going on. Back in the diagram. So while this is running, you can see things are kind of moving around. And what's happening is that some actors, they kind of pop out of existence. You can see them, they get a little bit bigger and fade out. So they're kind of a nova, like a supernova, like a star going out. And then you can see new actors coming in. They're highlighted in dark color for a moment when an actor is first started. So what's happening is the actors stay alive while they're receiving messages. If they don't receive any messages after a certain period of time, these actors shut themselves down. So I've set the timing on how often messages are sent so that get a little bit of this coming and going of individual entity actors that kind of show actors stay in memory as long as they're receiving messages. But if they're after a configurable amount of time where no messages have been received, the actors will shut themselves down, or what's called passivate themselves. So that's what we're seeing here. But what the trick, though, is that my browser is sending in requests via Node 2. So this web page is sending in HTTP requests to Node 2 to get JSON responses back to tell it what's running in the cluster so it can build this tree. But the real challenge is that, say these two actors that are dark, they just started on this other node in the cluster. So how does the fact that these two guys just started on node 9 get communicated to node 2? Well, what's happening on node 9 is these two actors that just started send a message to a single actor that's running on node 9, the HTTP server actor, and saying, hey, I started. The HTTP server actor running on node 9 gets that message, and it broadcasts it to all the other nodes in the cluster. And I'll give you a moment to guess, how did I do that? And if you were paying attention, if anybody's out there, I don't know if anybody's out there or not, I use a receptionist. So the broadcast, the HTTP server actor registers and subscribes with the receptionist to say, hey, I'm here. And when I receive messages that new entity actors have started or stopped, I'm going to send notification message to all of my counterparts across the cluster. And I'm using a receptionist to do that. And then now the HTTP server has that data. So if I move this viewer to a different port, which I can do by just changing the port, I'll show you. I'll go to 255.4. Oops, come on. There we go. I'm hitting a different HTTP server. See, now 2554 is highlighted with a lighter color. So, but I'm still seeing the whole tree. So the trick with this project that was fun to implement, but it wasn't super hard for me to do it as a developer. I'm just a developer. I'm not an Akka, engineer. I want to do cool stuff like this, is that it was fairly trivial for me to write my own code that did this, whereas new actors are starting up, all the other HTTP server actors and the server itself have a I'm building a tree basically of all this information. So this tree of what this tree that's represented in a circle is a data structure that's being maintained in all 9 nodes in the cluster, or however many nodes are in the running cluster. I guess in this case it's 7. So if you look at the HTTP server actor, we should see where it receives a broadcast message. And if we look at the on broadcast, it is just looping through the list of service instances that it's been maintaining using the receptionist. So I'll leave that as an exercise for you guys if you're interested to jump through that. But that's what's going on here. I'll put in, I hope I got some of that across. It's a very, very cool. This is starting to get much deeper into Akka, but it's not, again, rocket science. So this project has the two dashboards. It has the dashboard we've been looking at throughout this whole thing, and now it has this viewer. So let's move on. I'm going to stop this guy. Cluster. We should see all the nodes shut down and the tree go completely away. Boom, there it goes. It's gone. All right, and then I'm going to stop this guy, and then wait for everybody to shut down. Go away. Stop. There we go. All right. There's another app, and it's already running. I'm going to show you right here. More eye candy. This is another AkkaCluster demo application. It's composed of actually 2 repos, 2 projects that work together as a single application, 2 Akka microservices, basically. The UI is included. The UI you're seeing here is just some JavaScript that I wrote that is included with these projects. And it's currently running on, this is running in an Amazon environment. And it's also using a database. I'm using a lot of the things that I just showed you in the previous projects. In this project, I'm using cluster singletons, I'm using cluster awareness, I'm certainly using cluster sharding, and I'm running things at scale here, because what we're looking at is a map of the world. And this is a simulation or a demonstration of like a basic IoT, Internet of Things type of an application. So with this demo application, what you can do is you can zoom around this map. It's like a Google map, and you can create IoT devices in different geographic regions around the world, pretty much wherever you want, including in the water if you wanted to do that. So you can see that there's these markers that are distributed in different places around the world. And what they indicate is where I previously populated some IoT devices in these different geographic locations. If you look at the bottom left and right, there's counters that tell how many devices are created. So on the left, it says how many devices are in view, and it's 209,000 devices are in view. And on the right, it gives just a worldwide count, because as I zoom around the map, it's going to show, what's in view will change. But as I mouse around, it gives me information. So I mouse around this region in South America, and it says that there's a total of 37,000 IoT devices that have been created in this geographic region. And every IoT device has a very simple state. It can be either happy, green, or it can be sad, red. So in this case, the marker is showing yellow because some of the devices are sad and some of the devices are happy. And it's saying that there's 1,344 that are sad. So all the data that I'm getting on the map is coming from the back-end Akka microservices. We're using things like cluster sharding, cluster singleton, and so on. If I go to different regions in the world, there's 5,000 and a couple markers here. Down in Mexico, I think there's 6,000, 10,000 in the San Francisco area, 16,000, and so on. And just for grins, because this is a conference in Kiev, which I really wish I was there. I love coming to Kiev. But I created some devices in this region, but there's only 64 devices. So what I can do, though, is I can zoom in. And the way this works is that now you can see on the left, it shows that there's only 64 devices shown in view. But there's still, of course, there's still 209,000 worldwide. Up on the top left of the screen, there's some information. It shows a zoom level. As I zoom out, it goes to a higher number. As I zoom in, it goes to a lower number. So the lowest number, of course, is zoom 1. The highest number is zoom 16. My mouse, when I move my mouse around, the latitude and longitude of where my mouse is pointing changes. And then there's this other indicator which says device density. And what this means is that if you can see that there's this grid that's superimposed over the map, which, by the way, is being done by JavaScript that I wrote that's provided with this project. So this grid, each grid region, the way this app works, I could place 1 million devices in this region. So in the region where there's currently only 64 devices in the Kiev area, I could potentially create 1 million devices. Then in the top right, when I zoomed in, this other thing appeared, which shows some information. It's like a little menu, and it shows that there's a rate setting. Capital R increases the rate, lowercase r decreases the rate, and the rate is set at 1,000 per second. I'll explain what that is in a minute. And then you can type a C for create, a D for delete, a H for happy, and an S for sad. So what's going on here? So let me zoom into the Kiev area a little bit more. You should zoom into the point. There it goes. The marker, when I zoom in close enough, the marker changes to the region where there's devices. So you can see in this region, there's 64 devices. If I zoom in more, the resolution gets lower. So it's 4 regions of 16 devices. know, 16 regions of 4 devices. So at every zoom level halves, or the area is reduced by 3/4. So this big region, when I zoomed out, it went 64 to 16 to 4 to 1. So this is as far as I can zoom in. The zoom level is 1. So what this means is that here, and I'm kind of at the city street level, that there's 1 device per region here. And so the idea is that with this demo app, I want to generate load. And the way I can do that is that I zoom out a little bit and say I want to create some more devices. So I'm zoomed out, so the device density is 64. If I type a C, if I move my mouse around, it highlights the area where if I click, it's going to create devices there. So if I click this region right next to the one I created before, we should see some device. There they go. They start showing up. So now there's 16, 16, 16, 16. So I created 64 devices. Big deal. I mean, I can zoom all the way down and create 1 device. And what's happening is the request goes into, there's a couple of microservices. It actually goes through one microservice into another microservice, and when it's done, we see the result. But this is boring, creating 1 device, creating 16 devices. Let's get a little bit more adventurous. I'm zoomed out. Now I want to create, say, 256 devices. So if I do a create, now 64 already exists, so it's not going to recreate those. But we should see devices get created. There you go. So now I've put some load on the system. I just sent in requests to create 256 devices. So this is like, say you have say this is a shopping cart app, just for a moment. This is really an IoT app, but say it's a shopping cart app, and there's customers in 64 customers in each of these regions. So it's like 64 customers hit the buy button right now, and they all said, I want to buy what's in my shopping cart. So we're generating that load. So the goal of this project is to generate load, but to visually show that load getting generated. So now I'm zoomed out even more to where the device density is 4096. So I can do the same thing. I'm going to hit create, but now a couple things. The rate is set to 1,000 per second. And if you notice at the top, I don't know if you can see it, but it says 4 seconds. So it's giving me a clue that it's going to stagger the creation excuse me, of these 4,000 devices over 4 seconds. So I'm going to click it. I'll zoom in a little bit, and we should be able to watch the devices get created over this region. So 4,000 requests came in to the backend services. 4,000, there's a microservice sitting back there that received 4,000 gRPC messages, and it processed those messages. It updated databases, and then when the database, all the updating of the databases was complete, we saw the data on the map here. So the delay there that you're seeing is a kind of an eventual consistency delay, because the microservice that I'm using is using CQRS, Command Query Responsibility Segregation. If you're not familiar with it, it's a very, very interesting topic. Certainly won't have a lot of time to get into it here, but because I kind of want to just show you the mechanics of what's going on. But the backend microservice is receiving all those HTTP requests and processing them. And I can do similar things. I mean, so I've just created 4,352 devices now exist in this region. I can zoom out again, and another 4096, and just for fun, I'll do it. Well, let me show you something else. I'm going to zoom into 1024. So it should just be 1 second, but I'm going to submit that, and I'm going to move, type C, submit another one, move and type C, submit another one, move and type C, submit another one. So this is another thing I mean, it's pretty easy to overwhelm the backend system with this demo app, because I can very quickly generate a lot of load. So now we've got 8,000 devices in this region. Now, the other thing I can do is I can make some SADs. I'm going to zoom in a little bit more. So if I type an S, move around, if I click, it's sending messages to the existing IoT devices that are in the backend service, and it's saying, change your state to SAD. And there we go. We're starting to see some of the changes. And here we go. So the changes are going through. I could do another one. Oops, now I want to do a SAD. So this is running on, like I said, it's running on Amazon. I'm using Cassandra for, if you know CQRS, there's a write side and a read side. There's an event. The right side has an event log, which is a very simple data structure. I'm using Cassandra for the event log. And then for the read side, which is the data that we're seeing here, I'm using Postgres, a SQL database. So what's happening is both those databases are getting updated here. We're looking at the data coming from the Postgres database here. Create some more SAD. I can zoom in, and maybe I'll make some of these happy. It should change them to green. So this project has been a blast to implement. The UI was fun. Yeah, I didn't really call it out, but there's a kind of an activity indicator that's in the middle here. It's showing some rates of a creation rate of about 1,000 per second, which is kind of where we were set. There was some spikes where there was 1,000 per second created, things like that. So let's go and look at the projects. There's two projects. It's called Where on Earth, WOE. So if you look in, actually, let me go to GitHub, and I'll show you the repos. So there's one project. I got to fix the name of this one. It's called What on Earth, but it doesn't really matter. It's called Where on Earth Sim, and then there's another repo called Where on Earth Twin. Like I say, these two work together. So it's when you the READMEs have instructions about how to set this up to run on Minikube on your own laptop, or I've run it in Google. I've run it in GKE, Google Cloud Engine, I think it's called, and Amazon EKS, Elastic Kubernetes Service. I've used different databases, different database engine back engines, but these are the two projects. So the simulator project is simulating the outside world. So it's actually when I send in a request to create devices or delete devices or change the state of devices, the simulator first gets that request, and then it changes or it takes that request and builds up all the individual requests for every single device. And then the twin service is the thing that's actually handling the state of the individual devices. The reason I call it a twin is there's some folks at Tesla that are doing some really cool work with Akka and IoT, and they coined the term digital twin. And I just love that term. So, to me, the way they explained it was, you have a physical device, an IoT device, say a battery, like a Tesla battery. In the real world, on the back end systems, there's one or more digital twin devices. It has a state about that battery back in the back end system. So it's a twin. So I just kind of use that term, twins. So back in the map, what happens is that when I do a click here, say to send in a request to create 1,024 devices, that goes into the simulator service as a single simple HTTP request. And it's basically saying create devices in this region on a map. And a region is defined by its top left longitude and latitude and its bottom right longitude and latitude. So, and of course the zoom level. So those 3 pieces of information, or actually 5 pieces of information, describe a region on the globe. And when the simulator service receives that, it cascades that into 1,024 gRPC requests from the simulator service to the twin service. So the simulator service has a gRPC client, and the twin service has a gRPC server. Now, the project is configurable to do HTTP as well, so I can, it's just a configuration setting to switch back and forth between the two. But I was experimenting with gRPC versus HTTP because I'm doing the service is doing a lot of messaging. In fact, let me zoom out to the full world again. There's 217,000 devices that are have been created. The way Akka is running here is that all 217 devices have an actor on the backend system. And all those actors are alive right now. This is by design by me, the implementer of this application. But the point I'm trying to make is that I've got an Akka cluster running, actually 2 Akka clusters running, 1 for each service. They're not too big. I think there's like 5 or 6 nodes running on the back end. And they're handling 200,000, each Akka cluster is handling 200,000 plus live actors. And the sim service is, if it's not sending commands to say create devices or delete devices or change the state of devices, it's periodically sending telemetry messages, a ping message basically, to kind of simulate you got a real device in the world that's periodically sending in telemetry messages saying, say it's a temperature sensor or a battery charge level sensor. My charge is 50%, and it sends that in every minute. And then, so it sends in 50% the next minute. My charge is 50%. The state hasn't changed of the device, so nothing happens on the back end, other than the fact that the back end system knows that that battery is still communicating because it just received a message from it. So in this demonstration app, I'm sending every minute, every single device from the simulator is sending a gRPC message to the twin service. This is around 3,000 messages per second that are running right now. And it's running on about, I think, like I said, I play with the scale, but it's fairly modest. I think it's like a 5 or 6 node clusters on each side. I don't know what it is. I haven't looked at for a while, but like I said, it's scaled it up and down. But it is fairly modest. But this is a lot of traffic. And it can also generate a lot of database traffic, right? Because when you do create devices or do some kind of a state change that requires some persistence, this is going to put a real strain on databases. And I'm using this demo app to also kind of explore the limits of different databases, like Cassandra, say Cassandra running in key spaces on Amazon, which has quite a bit of capacity, say, compared to maybe my own setup of Cassandra or a different setup of Cassandra. On Google, I haven't tried it yet, but I'm going to be hopefully soon testing with Google Spanner for a backend database, things like that. But let's look at these projects. So this is the main. And the main should be very familiar. It's kind of a similar pattern. In fact, I'm even using that cluster listener actor that I've been using all the prior projects. Oh, I'm sorry, I'm in the wrong project. Let me go back here and I'll go to the sim project. Sorry, here we go. Now we're in the main. So sorry, it is a little bit different. The So I start up an active system, and then I'm starting up a number of things. I'm starting up the Akka cluster bootstrap, starting up the HTTP server, and I'm also starting up a singleton. I call it a region pinger. The singleton running on the simulator is the thing that triggers sending telemetry messages every minute. And how that works is very cool. I wish I had the time to go into it. It really takes advantage of Akka. But I'm using cluster sharding here, and that's what I want to show you. So the same thing we saw earlier in the last project using cluster sharding, and very similar. Not, but other than the fact that I'm dealing with some databases. But I've got a cluster sharding setting up, and I have an entity actor, which is I call region. And the region actor is a little different because it's extending a base class called event source behavior. And this is what's called Akka persistence, because in this case, when these actors receive messages that trigger a state change, that's going to trigger persisting state change events to an event store in Cassandra in this current setup. So this is using Akka persistence. Because the simulator service is also keeping track of the regions of the map where devices have been selected. So if I stop this application and restart it, it's going to pick up where it left off. It knows that there's 209 or 200, however many thousand devices. It knows the locations of them, and so the simulator service can be restarted and it can pick up where it left off. I also need the persistence because this is running in an Akka cluster and nodes can come and go. But the messaging, and so on is all done in the same way that we just saw. And the last thing I want to show you, I only have a few minutes left, is kind of the backbone of this. So again, these projects are here. This one's it's set up for you to take. I've got instructions where you could say set up Minikube, set up your Cassandra, set up Postgres on your local system, and make it work. It definitely takes some work to do it, but you can get the map running. And then the map UI you can pull up in a browser. I've got it all defined. I've also got instructions for deploying it to Akka or to Amazon and Google. Those things are kind of a work in progress right now. I'm cleaning up some of the READMEs in these repos. These guys are definitely a work in project. But the map itself is a very fun way to do things. And if you're looking for something to generate some load, this thing can do it. But to finish things up, I want to move on to a final project, which is this guy. Like I said, I just got this working the way I wanted yesterday. So it should be familiar. It's the crop circle. In fact, let me turn a bunch of this stuff off for a moment. But what's happening though is that this thing's running in Kubernetes. And I'm actually using two Akka clusters here. So the Akka clusters are represented on the left and the right. So on the left, this shows the cluster sharding application and is currently running with 5 nodes. And I'm showing like the IPs and the number of messages that each of these nodes has processed. On the right, I've got another Akka cluster that's a simulator. So what this guy is doing is real simple, but I wanted to be able to scale up the amount of traffic easily. So if I scale up the number of nodes running this cluster or scale it down, I increase or decrease the traffic from this cluster, which is sending HTTP messages to this cluster, the cluster sharding cluster. So it's a familiar, cluster sharding diagram. I'm not using a database here, but what I wanted to show you is this is kind of the anatomy of the Where on Earth demo application. The Where on Earth is using cluster sharding. It's an integral part of the way it works. But I wanted to have a way to visualize some of the traffic. So if I click one of these nodes, I can toggle on or off what's happening. So what I'm showing here is that HTTP requests are coming in from all of these different nodes, all these different IPs at varying rates, and the requests are going in through a load balancer. So what I'm showing is that I'm tracking the requests that came in from these guys that landed on this one node in the cluster, just this one node right here. So what's happening is these are commands coming in for specific entities here. And then these lines that are radiating out from the node to the entities are showing the actual entities that these guys are talking to. And you can see that the lines are changing because the messaging is changing. So I'm tracking like the last 50 messages that this guy has received, and I'm visualizing it here. But you can see that different actors are getting hit. But what the flow is showing here is that these are messages getting sent in from all these guys. It landed on this node, and it's saying, hey, I want to send a command to entity like whatever, like this guy. And yeah, it can click to trace it. So, no line is coming into that, and that actor just went away. So let me click another one. I know I'm just about out of time. But so it's just showing the distribution work. So messages come into this node, and then it could talk to entity actors that are running on that node, or it could forward those messages to entity actors running on other nodes in the cluster. So this gives you a little bit more, hopefully, intuition about the flow. So I can turn off and turn on individual nodes. And so now that I'm following the messaging on this node, and I can just go crazy and turn them all on. So that the visualization piece was the last thing I got running. So it's just really showing that the environment of routing messages that's handled by Akka is pretty wild, pretty sophisticated. But the programming to do it for us as developers is quite simple. And this also is another project that's available. Let me go back to the GitHub. Sorry. It's called Simulator and Visualizer. So it's Akka Cluster Kubernetes Visualizer and Akka Cluster Kubernetes Simulator. Work in progress. I've got documentation on setting it up in OpenShift on it's called Code Ready Containers, and on Minikube, just Kubernetes. So I think I've used up all my time. I really appreciate if anybody's hung in there through the whole thing, and I'm done.
Hi, Hugh. Thank you very much for your speech. Sorry for our agenda and that we should finish your speech, but you can continue the communication in Q&A Zoom room. And also, if participants have some questions, you can answer here too. Thank you very much, Hugh.
Thank you.